Alright, let's go. Number 10. The double-slit rendering problem. Thomas Young in 1801 was trying to end a bar fight between dead physicists. Isaac Newton had insisted for over a century that light was made of tiny particles moving in straight lines. A handful of contrarians thought light was a wave. Young wasn't trying to break physics. He cut two narrow slits in a piece of card, shunned sunlight through them, and expected the pattern on the wall behind to settle the argument for good. The prediction was clean. If light was particles, the screen would show two bright bars, one directly behind each slit, like paint sprayed through two nozzles. If light was a wave, the screen would show the interference pattern waves make when they overlap, a stack of alternating bright and dark stripes, spreading outward the way ripples do when two stones hit a pond at the same instant. Two possible outcomes, one experiment. That was the appeal. Young got the ripples. Light was a wave. Century closed. Textbook rewritten. Then, in the 20th century, physicists ran the same experiment with single electrons, solid particles, fired one at a time. One electron leaves the gun. One dot appears on the detector. Do that thousands of times. What emerged on the screen made no sense. The dots slowly built the interference pattern of waves. Each individual electron was passing through both slits and interfering with itself. Akira Tanemura at Hitachi published the definitive single-electron version in 1989 in the American Journal of Physics. And here's the part that has never stopped disturbing physicists. The moment you place a detector at the slits to see which slit the electron actually goes through, the interference pattern vanishes. The electron picks a lane. The wave behavior evaporates. Every proposed explanation carries a cost nobody wants to pay. Niels Bohr's Copenhagen interpretation says, the electron has no defined position until measured, which quietly smuggles the act of observation into the laws of physics themselves. Hugh Everett's Many Worlds interpretation, published in 1957, keeps the math clean by splitting the universe every time anyone looks at anything, which most physicists find philosophically unbearable. David Bohm's pilot wave theory brings back hidden variables, but John Bell's later theorem would eventually rule out the simple version of that route. Decades in, no interpretation feels complete. Every atom in your body runs on this same quantum machinery. When nobody is measuring, your fingernails and neurons operate under the rule that reality only settles into a definite state when something checks. That applies to you as much as it applies to a laboratory electron. So who exactly counts as an observer here? And why does a strip of measuring equipment qualify when a wall of interstellar dust apparently does not? If reality only resolves when observed, the next question is how finely it can resolve at all. Number 9. The pixel size of reality. Around 1899, Max Planck sat down with a bureaucratic problem. He wanted to define a system of natural units that any civilization anywhere in the universe could derive from scratch, without needing to know what a meter or a kilogram or a second actually was. He took three of the most fundamental constants in physics, the speed of light, the gravitational constant, and his own quantum of action, and combined them until they produced units of length, mass, and time on their own. The idea was mundane. He was building a measuring stick, not a theory of everything. The predicted behavior of the numbers he pulled out was simple. They'd be small, universal, and useful for cleaning up equations. What he wasn't expecting was that one of those numbers, the unit of length, would turn out to represent a hard floor on how small a distance the laws of physics could even meaningfully talk about. That number is roughly 1.6 × 10⁻⁵ meters. Below that scale, general relativity and quantum mechanics stop agreeing with each other so violently that the concept of distance itself starts to lose meaning. To put that in scale, the proton, which is already about 100,000 times smaller than the atom it sits inside, is still 10 OPU times larger than the Planck length. It's the smallest distance any current physical theory can describe. John Wheeler, who coined the term quantum foam in the 1950s, described what happens below this scale. Space stops behaving like a smooth sheet and starts behaving like a seething, chaotic froth of quantum fluctuations. Every attempt to describe what happens under that floor has failed differently. String theory tried to replace point particles with tiny loops of vibrating string, and 40 years in, it has still not produced a testable prediction that anyone has confirmed in a lab. Loop quantum gravity proposed that space itself is woven from discrete units, but has struggled to cleanly recover the smooth spacetime we see around us at ordinary scales. Causal dynamical triangulation, condensed matter analogues, emergent gravity, each one describes a different way spacetime might be built from something more fundamental, and none of them agree on what that something is. Now consider this. Every digital image has a resolution, a smallest possible unit of information, below which the picture simply stops. The Planck length behaves the same way for space. Nothing in physics forces reality to have a smallest unit, and yet apparently it does. Why should space have a pixel size at all? And what exactly is being displayed at a resolution finer than physics is allowed to see? Zoom back out from the pixel scale, and something even stranger shows up at the opposite end. Number 8. The connection that ignores distance. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen sat down to write a paper that would embarrass quantum mechanics. Einstein hated the theory's implication that a particle could have no definite properties until measured. The three of them constructed a thought experiment they were sure would expose the whole framework as incomplete. Take two particles, create them in a correlated pair, then move them light years apart. Measure one. According to quantum mechanics, the other should instantly reflect a correlated result. The setup was designed to force a choice. If quantum mechanics was right, then measuring one particle would somehow influence its partner faster than the speed of light, a violation of special relativity, which was Einstein's own theory. If quantum mechanics was incomplete, then the particles must have carried the answer with them the whole time, like a pair of gloves in sealed boxes. Einstein was betting on the gloves. He was wrong. Experiment after experiment showed the particles genuinely did not carry the answer. The correlations held regardless of distance, and no signal was traveling between them in any conventional sense. In 2017, a team led by Pan-Jian Wei at the University of Science and Technology of China used the MISHIS satellite to distribute entangled photons between two ground stations separated by 1,203 kilometers. The results were published in Science that same year. The entangled pairs remained correlated at that distance, with no measurable delay. Later experiments have pushed further. The effect does not weaken with separation. Every attempt to explain this away has been closed off, one root at a time. Local hidden variables were ruled out by John Bell's theorem in 1964 and its experimental confirmations. Superdeterminism, the escape hatch where the universe was rigged from the Big Bang to produce those correlations, is technically consistent, but requires abandoning the entire idea of free experimental choice. Retrocausality proposes that measurements send information backward in time, which most physicists find worse than the problem it solves. Many worlds handles entanglement elegantly, at the cost of infinite branching realities. Everything on the shelf carries a fee. The blood in your veins contains electrons, whose partners are now scattered across the observable universe, correlated with them through the same mechanism. Every cup of coffee you've ever drunk has done the same. This is not a lab curiosity. This is how ordinary matter behaves at the level it's actually built out of. If the particles are not communicating, and we're not carrying the answer, then what is enforcing the correlation across a distance of 1,000 kilometers with no time in between? Now shift from the strange rules of matter to the strange numerical values that govern how any of it works. Number 7. The constants that shouldn't fit. By 1953, Fred Hoyle was stuck on a problem in nuclear physics that had nothing to do with the meaning of existence. He was trying to figure out how carbon gets made inside stars. The nuclear physics of the time said carbon shouldn't form in appreciable amounts. The reactions involved were too inefficient. But carbon clearly existed. Your body is about 18% carbon by mass. Hoyle looked at the numbers and predicted that there had to be a very specific, previously unknown resonance in the carbon-12 nucleus at exactly 7.65 million electron volts. Otherwise, the universe should be almost carbon-free. The prediction was extremely narrow. He was calling his shot. Standard nuclear theory offered no reason for such a resonance to exist at exactly that energy. If Hoyle was wrong, the universe as we know it shouldn't work. If he was right, physics had a coincidence to explain. William Fowler ran the experiment at Caltech shortly after. The resonance was there. At almost exactly 7.65 MeV, within Hoyle's predicted window. The story didn't stop with carbon. Physicists spent the following decades tallying similar coincidences across the Standard Model. The strength of the strong nuclear force, the ratio of the electron and proton masses, the cosmological constant, the initial low-entropy state of the early universe. Martin Rees at Cambridge condensed 6 of them into a 1999 book called Just 6 Numbers. Each of these constants, tweaked by even a small fraction of a percent, would produce a universe with no stars, no chemistry, no possibility of anyone reading a sentence like this one. Every proposed explanation trades one uncomfortable idea for another. The anthropic principle says of course we observe values compatible with life, because we couldn't exist to observe otherwise, a statement most working physicists find suspiciously close to giving up. The multiverse hypothesis says our universe is one of an unimaginable number, and we happen to sit in a hospitable one, which shifts the coincidence problem into an unfalsifiable claim about universes we can never see. Some proposals invoke an as yet unknown deeper theory that forces these values, which is a promise, not an explanation. Others simply accept the coincidence and stop asking. None of these options are satisfying, and everyone in the field knows it. The atoms in your left hand are here because a nuclear resonance sits at 7.65 MeV, and not, say, 7.5. Shift that one number a fraction of a percent, and the periodic table above helium collapses. Your body would not have the raw material to exist. Why should a universe indifferent to life produce numbers so exquisitely tuned that a fraction of a percent nudge in any of them would erase every observer in it? The constants sit on a knife edge, and the geometry they operate in may not be shaped the way it looks. Number 6. The flat projection. Jacob Bekenstein spent the early 1970s doing careful thermodynamic accounting. He was a graduate student trying to figure out what happens to the entropy of a cup of coffee when you drop it into a black hole. The second law of thermodynamics says entropy in a closed system can only increase. If you throw the coffee across the event horizon and the black hole simply swallows it, the universe's total entropy appears to drop. Something had to be storing that lost information. Bekenstein proposed that the entropy of a black hole is proportional to the surface area of its event horizon, not its volume. Stephen Hawking initially disagreed, then in 1974 worked out the math for black hole radiation and confirmed the relationship. The information content of a black hole scales with the two-dimensional area of its boundary, not the three-dimensional space inside it. That was the strange result. Everyone assumed it was a quirk of black holes. It isn't. Gerard Hooft in 1993, followed by Leonard Susskind in a 1995 paper titled The World as a Hologram, generalized the finding. They proposed that the maximum information content of any three-dimensional region of space is fully encoded on its two-dimensional boundary. In 1997, Juan Maldacena published a specific mathematical version of this idea, the ADS/CFT correspondence, showing an exact equivalence between a gravitational theory in a certain higher dimensional space and a quantum field theory living on its lower dimensional boundary. His paper has been cited over 20,000 times, making it one of the most influential papers in modern theoretical physics. 2 of the most respected physicists alive proposed, and a third formalized, the idea that our three-dimensional experience of the world may be a projection of information stored on a distant two-dimensional surface. Every attempt to interpret what this actually means has struggled. Some physicists treat it as a mathematical duality, a useful trick, and no more. Others take it literally, in which case the interior of a black hole and the surface of it contain the same information twice, and the inside is in some sense not fundamental. Craig Hogan at Fermilab spent years running an experiment called the holometer, looking for tiny holographic noise in laser interferometers. The 2015 results showed no signal, which ruled out one specific model without touching the broader framework. No one has ever produced a clean experimental test of the general principle. The three-dimensional depth you're seeing right now, the sense that there's actual volume behind the screen and around your body, may be a compression artifact of information written on a surface you cannot see. If our universe is a projection, what is doing the projecting, and what is it projecting onto? If reality is a projection, the mismatch between what the projector should output and what we see gets worse from here. Number 5. The worst prediction in the history of physics. In the late 1990s, 2 rival teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z supernova search team, led by Brian Schmidt and Adam Rees, were doing routine cosmological work. They were measuring how the expansion of the universe was slowing down over time. Standard cosmological models predicted the expansion should be gradually decelerating under the pull of all the matter in the universe. The prediction was straightforward: track distant supernovae, compare their apparent brightness with their redshift, confirm the expected rate of deceleration, publish, move on. The supernovae came back too dim. That meant they were farther away than the models predicted. The expansion of the universe was not slowing down, it was accelerating. The results were independently confirmed and won the 2011 Nobel Prize in Physics. Something invisible, permeating all of space, was pushing outward with a nearly constant energy density. Physicists called it dark energy and identified it with the cosmological constant that Einstein had introduced in 1917 and then discarded. The measured value is small, roughly 6^10^1 joules per cubic meter. When quantum field theory tries to calculate what that vacuum energy density should be from first principles, the answer that comes out is somewhere between 1060 and 10^120 times larger than the observed number, depending on how the calculation is set up. That is a discrepancy of up to 120 orders of magnitude. Every attempt to close that gap has failed catastrophically. Supersymmetry would naturally cancel most of the offending vacuum contributions, but decades of searches at the Large Hadron Collider have found no supersymmetric partners, forcing physicists to keep pushing supersymmetric particle masses higher and diluting the cancellation. Anthropic selection within a landscape of possible vacua handwaves the problem into a multiverse. Modified gravity theories struggle to match precision cosmological data. Sean Carroll at Johns Hopkins has called it the most embarrassing prediction in physics. Steven Weinberg, the Nobel laureate, spent decades on it and before his death in 2021, admitted that no known mechanism cleanly explains the value we actually measure. That mismatch, a factor of 1 followed by up to 120 zeros between what our best theory predicts and what the sky actually shows, sits at the center of the cosmological model that governs everything from the birth of galaxies to the fate of the last star in the universe. It is the substrate the sky is built on. If our most successful physical theory is off by that margin on this one quantity, what else is it quietly wrong about? That gap between prediction and measurement is bad. This next result closes a door. Number 4. The theorem that shut the exit. John Stuart Bell worked at CERN. On his weekends in 1964, he thought about a problem most of his colleagues considered settled: Einstein's 1935 objection to quantum mechanics, that measurement outcomes were determined all along by hidden variables the theory just wasn't tracking, had lingered as a philosophical footnote. Bell was troubled that no one had tried to work out whether that view was mathematically testable. So on his own time he did. The setup was elegant. Bell showed that if any theory involving local hidden variables was correct, the statistical correlations between measurements on entangled particles would obey a specific mathematical inequality. Quantum mechanics predicted correlations that would violate the inequality. That gave physicists a clean, decidable question. Run the experiment, measure the correlations, see which side of the inequality the numbers landed on. The numbers landed on the quantum side, every single time. Alain Aspect at the Institut d'Optique in Paris ran the first rigorous experimental tests in 1982, closing several loopholes and confirming that quantum mechanics gave the right predictions. John Clauser had done earlier versions in the 1970s. Anton Zeilinger's group closed the remaining major loopholes in the 2010s. In 2022, the Nobel Prize in Physics was awarded jointly to Aspect, Clauser, and Zeilinger for this body of work. There is now no serious ambiguity. The universe cannot be both local, meaning nothing influences anything faster than light, and realistic in the classical sense of particles carrying definite properties before measurement. At least one of those assumptions is wrong. Every attempt to escape this conclusion has cost something the field wasn't willing to give up. Superdeterminism preserves both locality and realism, but requires that experimenters' choices were themselves determined billions of years ago in exact conspiracy with particle states. Technically consistent, but it dissolves the entire concept of a controlled scientific experiment. Non-local hidden variables in the style of David Bohm keep realism but throw out relativity's local structure. Many worlds keeps locality, but multiplies universes without limit. QBism reinterprets probabilities as subjective agent beliefs, which most physicists find suspicious for a theory that so accurately predicts measurements. No exit is free. The correlations that Bell's inequality forbids classical theories from producing are the same correlations that make the transistors in your phone work. Every text message, every photograph, every heartbeat monitored by a modern sensor rides on physical behavior that no local, classical theory can explain. If reality can't be both local and definite, and we've now confirmed that with Nobel Prize-level rigor, what is the actual thing we're living inside, once we stop calling it either? Once locality falls, the search for structure inside the underlying code becomes fair game. Number 3. The code in the equations. James Gates is a theoretical physicist who spent decades at the University of Maryland. He's now at Brown, working on supersymmetry, one of the leading candidates for physics beyond the Standard Model. His day job was extremely technical. He was constructing mathematical objects called adinkras, which are graphical representations of the equations that govern hypothetical supersymmetric particles. This was pure formal physics, worked out on chalkboards, with no obvious connection to anything spiritual, philosophical, or metaphysical. The prediction from within the field was mundane. Adinkras would help classify the symmetries of certain kinds of equations. They'd yield mathematical patterns and maybe some new algebra. That's what mathematical physics is supposed to produce. Abstract structures useful for organizing complicated theories. What Gates found instead were block linear self-dual error-correcting codes, buried in the mathematics of supersymmetric particle equations, structures that show up nowhere else in physics, but do show up in computer science, where they are used to prevent data corruption in transmission. Gates published this finding in a 2010 essay for Physics World, titled Symbols of Power, and in more formal papers with collaborators including Charles Doran. His public statements about the work are usually careful. He describes what he found, error-correcting codes embedded in the equations that describe supersymmetric physics, and states clearly that he does not know why they're there. He avoids the strong claim that the universe is a simulation. And it needs saying, this whole line of thought is contested. Many physicists interpret the codes as coincidental mathematical structure without deeper meaning. Others take it more seriously. The debate is genuinely open and worth flagging as unsettled. Every attempted interpretation raises problems. Reading the codes as literal evidence of a simulation overreaches. Similar mathematical structures appear in unrelated pure math contexts, so their presence in physics equations is suggestive at best. Dismissing them as coincidence has to account for how tightly they embed into the supersymmetric framework. Deriving them from a deeper physical principle has never been done. Nobody has yet shown a natural physical reason for that particular kind of error-correcting code to appear in these equations. And supersymmetry itself remains unconfirmed at the Large Hadron Collider, which complicates the whole discussion. The mathematics that governs the deepest layers of matter, if supersymmetry turns out to be real, appears to contain structures we invented to make computers reliable. That is either a stunning coincidence or a hint. Nobody in the field has decided which, and nobody has a way to force the decision. If our deepest equations contain patterns identical to human-designed error correction, is that a fingerprint of underlying computation, or an accident of mathematical taxonomy that means nothing at all? Physicists finding code-like structures in the math is one thing. The formal argument for a simulation is another. Number 2. The philosophical trilemma. Nick Bostrom, a philosopher at the University of Oxford, published a paper in 2003 in the journal Philosophical Quarterly titled "Are You Living in a Computer Simulation?" He was not making a movie pitch. He was constructing a formal probability argument built on a chain of premises that most working philosophers of mind and computer scientists find individually defensible. The structure of the argument is a trilemma. Bostrom proposed that at least one of three statements has to be true. Either almost all civilizations at our stage of development go extinct before reaching the technological capacity to run high-fidelity ancestor simulations, or civilizations that reach that capacity almost always choose, for whatever ethical or practical reason, not to run such simulations. Or we are almost certainly living in one right now. The logic runs like this. If any civilization ever runs even one ancestor simulation containing conscious observers, they will almost certainly run many. The number of simulated observers will vastly outnumber the biological ones. Any given observer, including you, is therefore statistically far more likely to be simulated than not. This is worth separating cleanly from the pop culture matrix framing. Bostrom's version is a formal probability calculation. If you accept certain premises about consciousness being substrate independent, and certain premises about future civilizations being technologically capable, the probability calculation lands where it lands. The paper has been debated for over 20 years across philosophy departments, and by people including David Chalmers, who devoted significant attention to it in his 2022 book Reality Plus. Bostrom himself is careful to note that the argument does not tell us which of the three options is true, only that one of them must be. Every attempt to break the trilemma has failed to convince a majority in the field. Rejecting substrate-independent consciousness, the idea that a sufficiently detailed simulation of a brain would also be conscious, leans on assumptions about mind that no one has been able to justify from physics. Arguing that no civilization ever reaches simulation capacity requires believing every intelligent species self-destructs or plateaus, forever, without exception. Arguing that every capable civilization decides not to simulate requires a universal ethical consensus we have never seen humans achieve on anything. Each escape route requires a very strong claim about a universe we know very little about. If Bostrom's premises hold, then the odds that the atoms in your chair, the words you're reading, and the mind reading them are baseline physical, rather than computed drop below 1 in millions. Which of the three options do you actually believe, and how much of that belief is evidence, and how much is preference? The argument only bites if we can never rule it out, and we can't. Number 1. The test that can't be run. Silas Bean, along with Zora Davuti and Martin Savage, published a paper in 2012 titled Constraints on the Universe as a Numerical Simulation. Their idea was concrete. If the universe is being computed on some enormous underlying lattice, the way physicists themselves simulate quantum chromodynamics on discrete grids, then that lattice should leave detectable fingerprints in the behavior of very high-energy cosmic rays. Specifically, the highest energy cosmic rays should show a subtle anisotropy, a preference for traveling along certain directions relative to the underlying grid. The setup was rigorous. They calculated exactly what signatures a lattice simulation would produce at cosmic ray energies above around 5 × 10 1-bound electron volts. They laid out how the anisotropy would look. They proposed how to look for it. It was an actual empirical program, not a metaphor. The search continues. No confirming signal has been found, and that is where the problem gets uncomfortable. Every experimental proposal for detecting a simulated universe suffers from the same defect. Any signature you can propose, a lattice artifact, a computational shortcut, a rendering delay, a precision limit, could exist in a simulation, or in a base reality that just happens to have those properties. There is no observation whose presence would prove we are simulated, because a base reality could produce it. And there is no observation whose absence would prove we aren't, because a sufficiently good simulation could hide it. Silicon substrate observers designing tests to detect their own silicon substrate is a problem with no obvious solution. Every approach to fixing this has hit the same wall. Looking for lattice signatures assumes the simulation uses a lattice, which a competent simulator would not. Looking for computational shortcuts assumes the simulators cut corners, which contradicts the premise of a high-fidelity simulation. Looking for glitches assumes an imperfect implementation, which conflicts with the argument's own premises. Philosophers, including David Chalmers, have pointed out that the entire question may sit on the wrong side of the falsifiability line Karl Popper drew for science, meaning it is not a scientific question at all, but a metaphysical one. And metaphysical questions are the ones that never close. Every belief you hold about the world outside your skull is inherited from measurements you or someone else has made. All of those measurements were made from inside the system they were trying to describe. That constraint applies to every mind that has ever existed. It applies to yours right now. The reason the simulation hypothesis is disturbing is not because it's true, because there is no way to prove it isn't. Every anomaly on this list sits at the center of our best-tested theories, not at their edges. The double-slit entanglement, Bell's inequality, the cosmological constant, the fine-tuned constants, the holographic bound, these are not fringe results. They are the load-bearing structure of modern physics. The universe is not confused. We are. Each of these gaps is a place where the map contradicts the territory, and we have spent a century staring without finding the joint that would explain the mismatch. Whatever we're inside, we still do not know what it is. If you want to see more videos like this, click the video on screen now.